In this lecture, we are committed to discuss chronic-penny model of band theory. If I ask you, how can we tell a material behaves as a conductor or semiconductor? Definitely you will tell me by looking at the band gap, we can say whether the material is a semiconductor or conductor, right? But what if I could have asked you, why does a material, why does a material become a conductor, semiconductor or insulator? I know you don't have answer on this why, but this chronic panic model does have. It will explain why does a material become a conductor. Basically, it will help us to understand the device behavior. When an electron moves within a crystal, it has to face the periodic potential. You know that crystals are made up of atoms. Atoms are periodically arranged in a crystal. Each atom has their own potential. Atoms are affected by the neighboring one. Therefore, each atom has to communicate with the neighboring one. And or we can say the atoms are in interaction. Therefore, each atom has to share their potential with the neighboring one. Therefore, their potential structure becomes like that. As the electron has as the electron has to move within a crystal, as you can see, when they are in interaction, it has the potential structure like that. Let's say this region is 1 and this region is 2, and we can come to see that it has the repeating pattern of potential well and the potential barrier. Therefore, the electron has to face the potential periodic potential when it has to move through a crystal. And the thing is, the potential for region 1 is different and the potential for region 2 also different. How can we formulate the total energy of the electron in a crystal? Kinetic energy plus potential energy, right? As I told you, the potential energy of the electron has a variation when it moves in a crystal. Therefore, if the potential energy increased, definitely the kinetic energy has to be decreased. Why? Because throughout the system, total electron energy of the system is constant, since the energy is conserved. Therefore, if potential energy is increased, the kinetic energy has to be decreased, and the vice versa as well. As if the potential energy decreases, then the kinetic energy will be increased. When the electron moves, right, it will have the kinetic energy half mv square. If the kinetic energy needs to be increased, the velocity of the electron should be increased. Yes, if the velocity of the electron increases, definitely it will conduct more current in a device. When an electron moves in the presence of external electric field, the electron will gain velocity. This velocity is referred as drift velocity, and the current conduction by the drift velocity is called drift current. In semiconductor device physics, drift velocity and drift current is the backbone, right? In the whole lecture series, we'll be talking about electron and the potential, right? Before going into chronic penny model, we must know a wave function, right? So before knowing also wave function, we must discuss wave-particle duality. Wave-particle duality will help us to understand how the wave function comes to the picture. And before wave-particle duality, we must go through the history of the quantum mechanics. When we already had the classical mechanics, then what makes the quantum mechanics comes to the picture? History is a bit long. History tells that from the early 17th to late 19th, it was always been a confusion that some experiments prove that light is a wave, and some experiment proves that light behaves as a particle. And this creates the confusion to the reader. Reader used to think that today light will behave as a wave, yesterday light will behave as a particle. Right? So yeah, it's a bit confusing, right? So this confusion was resolved out by de Broglie, and this de Broglie suggested wave particle duality. Now let's begin with the confusion. It will have more fun. In 1801, Thomas Young's demonstrate YDSE, and it proves that light is a wave. In this experiment, we just need a monochromatic source of light and a slit and a screen. The source was placed in such a way that when it emerges spherical wavefront, as the spherical wavefront approaches the slits, the spherical wavefront gradually becoming a planar wavefront and hit on the slits. Okay, as it incident on the slits creates secondary spherical wavefront and hit on the screen. The observation was like a repeating pattern come to see, like bright fringe, dark fringe, bright fringe, dark fringe. So these things were come to see only for interference. You know, the interference comes to see only when it behaves as a wave. Therefore it is a property of wave, right? Property of wave. As a result, this experiment proves that light is a wave. Everything was going so smooth until and unless Blackbody radiation comes to the picture. The way we thought that light is a wave since YDSE proves, now the thing is going to be changed. In 1858, Kirchhoff introduced Blackbody. Kirchhoff introduces Blackbody radiation. Do you know what is blackbody? Everything in the universe is a blackbody who emits and absorbs all kind of radiation depending on the temperature. Now the studies has been done so far on the Blackbody radiations. In 1890s, two scientists, Leumer and Rubens, experimentally observed blackbody radiation spectrums. The observation was like that: when we plot spectral radiance versus wavelength, radiance is basically glow, how an object appears to your eyes, only. The observation was like, when we increase the temperature, the radiance peak has shifted, right, from the radiance peak has shifted from infrared to visible region up to 5000 degree Kelvin. We have the prime example for a black body like sun and the metallic rod. The sun emits radiation and you are able to see them. Okay, you are able to see the sun glows. Why? The sun emits most of the radiation in the visible region. That is why you are able to see them. And when you heat up the metallic rod more and more, the metallic rod starts glowing from red to violet, and you are able to see them because the metallic rod emits radiation in the visible region. And what about the human? Human also a black body, na? And the human also emits radiation at any time. But the thing is, human emits radiation, yes, but it emits radiation in infrared ray only. Our eyes are sensible to only visible region. We can't detect any radiation that emits in infrared region or UV region. What happens when we heat up the temperature more and more? Okay, it will start glowing from red and goes to violet. If it crosses the violet region, then it will step up in UV region. Therefore, when the metallic rod glows steps up into UV region, the glow will not appear to the observer or our eyes. Therefore, the glow of the metal would be faded out according to our observer or our observer eyes. Therefore, logically, the spectral radiance must have the peak, and the peak will be faded out when it crosses a sufficient wavelength, and when it crosses a certain wavelength, right? For that we got the experimental curve, but till that we did not have any theory that can prove the blackbody radiation curve that can fit those experimental curve. So in early 19th, Rayleigh and Jeans came up with experiment, and they tried to fit those curves from their equations like that. So they came up with equations like u nu d nu h pi c cube nu square kt, and the kt is the average energy in classical physics, right? And this equation was completely a failed equation. This equation could not able to fit those curves. So according to this equation, they observe this curve. So this curve doesn't even have a peak, right? So this expression or this theory is completely a failed model. So therefore, this curve is known as ultraviolet catastrophe. Ultraviolet catastrophe. So this curve could not able to explain the wavelength in ultraviolet region. So when we goes to the ultraviolet region, this curve has the infinite amount of intensity, which is not true biologically. And in 19 to prove those experimental curve in 1900, Max Planck comes to the picture. Max Planck suggested hypothetically when atoms vibrate in their lattice, in their mean position, they emit radiation. And originally it was believed that they emit radiation in continuous form, right? but Max Planck suggests that the energy emits but in a discrete mode, and it has the packet of quanta. It has the packet of quanta. It is a packet of quanta means like it has a discrete energy packets. Each energy packets have the energy of h nu. If there are n number of energy packet, then the total energy of the system is nh nu. So with the help of this theoretical expression, he got the average energy of the system, and he came up with equation like h nu e h nu kt minus 1. When he replaced this average energy with this formula, and he came up with such expression: h pi cq mu square h nu e h nu kt minus 1. And this formula was succeed to prove to explain those experimental curve. Equation was succeed to prove those three experimental curve even in at low temperature or at high temperature as well. As the curve was observed like that at high temperature, the curve has a peak in near to the visible region, and the peak was faded out. So exactly what we expected, he did it. So the blackbody radiation was explained by Planck successfully with the help of quantum mechanics. So he got the help of quantum mechanics, and he came up with average energy with the formulation of h nu e h nu kt minus 1, and he put that in this expression, and this expression was able to explain the blackbody radiation curve. And we already got the idea of E equals to nh nu. Okay. In 1905, with the help of this formula, Einstein demonstrate photoelectric effect. The observation was like that: when he incident light with a certain frequency, only at certain frequency, when it incident on the metal, the electrons are ejected out from the metal at only certain frequency. Okay, it is possible only when two particles collide with each other. Let's say this is a target particle and this the projectile particle collides with that. So this projectile particle collides with the target particle, and the target particles got scattered, right? So only and this target particle will be scattered only when the projectile particle will have the sufficient amount of energy, right? Similarly, also here we incident light with certain frequency mu, and it was seen that at this frequency the electrons are ejected out. Therefore, it has also energy of h nu. Therefore, this experiment proves us that light is a particle as well. As light is a particle, and this particle was named as photon, and this photon has the energy of individual photon has the energy of E h nu, right? So so YDSE probes light is a wave, and photoelectric probes, light is a particle, okay, light is a particle, and this creates confusion to the reader. Now this confusion is going to be resolved out by de Broglie in 1927. In 1924, de Broglie hypothetically suggests that if light means wave, if wave can behave as a particle, then why can't we say vice versa? Means why can't we say the particle can also behave like a wave? Yes, is it possible? If the particle moves with velocity v, definitely it will have the momentum, right? And when it is believed to be wave, definitely it must have to have the wavelength. De Broglie suggested a equation such that the momentum of an object is directly proportional to its 1 by lambda. To remove the proportionality sign, he introduced Planck constant, and it has the value of 6.63 into 10 to the power minus 13.4 joule second. If the particle if light behaves as a particle, it has the momentum. Sorry, if light behaves as a wave, it has to have a wavelength, right? Only so this single relation contains both of the wave and particle behavior, right? Therefore, this expression is referred as wave-particle duality relation. Wave-particle duality relation. This expression says that if a particle is in motion, it is associated with wave. It is associated with wave. Now, so this is a completely theory, right? In physics, we accept the theory only when it is been proved by the experiment. So basically, to prove this theory, in 1927, two scientists, Davisson and Germer, comes to the picture. You know the XRD, X-ray diffraction experiment. In X-ray diffraction, we take X-ray as a source, and we take the nickel and we allow the X-ray to fall on the nickel, right? And the X-ray was detected by the detector, and the detector was movable with an angle phi, and it has the angle of phi. Similarly, they did the exactly same, but the difference is only in X-ray. So they take electron beam instead of X-ray. Therefore, the observation was like that. They come to see the intensity has the variation. With respect to phi. Intensity was maximum at some angle. This angle was found out to be 50 degree. Intensity has, okay, so this intensity has variation only when it has interference. You know, interference is the property of waves. Therefore, this electron particle behaves as a wave. So therefore electron particles behaves as a wave, as de Broglie suggested. So therefore, if it is a particle, it has momentum and it should have to have a wavelength as well as. So this was proved by Davisson and Germer, and this is called wave-particle duality, right? So so we started from classical mechanics. YDSE proves light is a wave, and so when the blackbody radiation comes to the picture, yes, with the help of quantum mechanics, so the Max Planck was able to succeed to prove the blackbody radiation curve, and through the foundation of Max Planck in 1905, Einstein demonstrated photoelectric effect, and in photoelectric effect we observed that light behaves as a particle. And also in 1924, de Broglie hypothetically suggested a theory that if wave can behave as a particle, then also particle can also behave as a wave. And to prove this hypothetical relation, P equals to h lambda, in 1927, Davisson and Germer comes and they did it. They experimentally proved it. Yes, the particle can also behave as a wave, and this is called the wave-particle duality. So this is how the birth of quantum mechanics arises. So in the next lecture, we'll discuss a wave function, how the wave function comes to arises, how the wave function carries information regarding all the quantum particle like a photon, electron, like, and we'll start chronic penny model of band theory. Chronic penny model of band theory. Please be stay with me. Thank you for your patience. See you in the next class.